So let's define what is the greatest common divisor. So definition. So let A and B be two integers, not both 0. Then greatest common divisor is the greatest common divisor. That means what? Is the greatest integer or largest integer that divides both A and B. It is denoted by the greatest common divisor is denoted of A and B is denoted by GCD of A and B, or simply by A comma B, right? 1. Also, we can extend the definition to 0. GCD of 0 and 0 is 1, as GCD of A comma 0 is A for any A belonging to Z plus. That means set of all positive integers. Yeah, so we can extend this definition. Following this, we can extend this definition for GCD of 0 and 0, right? Now, a few examples could be that GCD of 26 and 39. Let's see what are all the integers which divide it and what is the largest among them. So GCD is usually positive, right? Unless it's both 0. In that case, if A and B both are 0, in that case, GCD of A and B is 0. But otherwise, GCD is a positive integer. So what are the divisors of 26 and 39? So the divisors of both 26 and 39 is actually 13 and 1, right? So GCD, so our divisors are rather common divisors of 26 and 39. So the largest one is, largest or greatest is 13. Therefore, example 2, GCD of 2 and 5 is 1. Right. So we call two numbers, so two integers A and B are called relatively prime or coprime if GCD of A and B is 1. Okay. So these are the definitions. So these are the definitions of GCD. It's a very useful object in whole of mathematics. We'll see that soon why. But before that, let's have some characterization of GCD. So theorem. So let's have first a result about GCD, that let A and B belong to Z such that GCD of A and B equals to D. Then we have A by D is going to be an integer because D divides A, so therefore D over A is going to be integer. Similarly, B by D is going to be an integer, But if you look at GCD of these two integers, it's going to be 1. Namely, in other words, they are relatively prime or they are co-prime. So the proof starts as follows. So let's prove this. Proof, let GCD of A and B equal to D. This implies D divides A and D divides B. This implies D, A by D and B by D are integers, right? So other than that, we can't really talk about GCD. We don't talk about GCD of non-integers, right? So now we want to show that there's no common divisors for this to except 1. So let E be any other positive divisor of A by D and B by D. So this would mean what? This implies, so E divides A by D implies there exists K1 belonging to Z such that E K1 equals to A by D. Similarly, E divides B by D would imply there exists K2 belonging to Z such that E K2 equals to B by D. But these would together imply that DE K1 equals to A and DE K2 equals to B. This means what? DE divides A and B, and so this would mean, but D is the largest divisor, right? So D is the largest divisor of A and B because it's a GCD. So this would mean DE is less than equal to D. So this is positive, this is positive. So the only way this can happen is that DE equals to D or E must be 1. So therefore, any other divisor of A by D and B by D is 1. So this would mean GCD of A by D and B by D is equal to 1. So that proves your claim. Okay. So now, based on this theorem, we can have the following corollary. If you take A and B non-zero integers, then A by B equals to P by Q for some integer P and Q non-zero such that GCD of P and Q equals to 1. Again, this is a corollary to the previous theorem. We can use that. So we get A by B equals to A divided by GCD of, let's say GCD, proof let GCD of A and B be D. Now this would mean A by D and B by D are relatively prime. So this implies, so let A be A by D be P and B by D be Q. So therefore we get A by B is same as divide top and bottom by D. This will be P and this will be Q. And from here we get with GCD of P and Q. So this proves the following, that if you take any positive integer, if you take any integers A and B, both non-zero, then you can write it in the lowest form. What does it mean by lowest form? You can write it as one integer P divided by another integer Q, where P and Q do not have any common factor except one. Okay. So now a few more results. So theorem, there are a few more properties of GCD, namely the following. Let A, B, and C belong to Z, then GCD of AB is same as GCD of A, B, but you can add some constant times B plus A plus CB, B. So how do we prove it? We can prove it the following way. We want to prove that these two are equal. So the way we can show is that let E be a common divisor for, say, A and B. This implies E divides A and E divides B. But we have seen an earlier theorem that E divides A and E divides B. E divides linear combination of A and B. In the divisibility chapter, we can say E divides then CB plus A as well. And of course, E divides B. So we get 1. That means what? That means E is, so E be a positive common divisor. Then we can say that E divides CB plus A and E divides B. So E is going to be less than equal to, because it's a common divisor for both, and GCD is the largest common divisor. So this would mean that it's going to be less than the greatest common divisor, which is A plus CB, comma B. So that is 1. Similarly, let F divide, so let F be a common divisor for what? For A and B. So let F be a common divisor for A plus CB and B. This implies F divides, again using the linear combination argument, A plus CB minus CB, and F divides B. This implies what? This implies F divides A and F divides B. This implies F divides, so F is a greatest common divisor. Sorry, F is less than equal to GCD or now from 1 and 2 our argument follows, because now E is basically less than equal to a plus b comma b, where e is any common divisor of a and b, right? So we get that any common divisor of a and b is going to be less than equal to GCD of a plus c and b. So now what is the upshot of that? So E was any common divisor, right? So this would mean F is less than equal to E, right? Because E was any common divisor. So in particular, B E can be equal to the GCD, right? So F is going to be less than equal to GCD of AB. So E is any common divisor, any positive common divisor. In particular, from here we can get that AB is going to be less than A plus CB, comma B. Similarly, let F be any common divisor for A plus CB and B. That means F is going to be less than equal to A GCD of AB. F is any common divisor, so in particular it can be the GCD of this guy. So GCD of A plus CB, comma B, going to be less than equal to AB. Now, if you combine these two, say star and hash, you would get that these two integers must be equal. So, right. So now, the nice property of greatest common divisor is that it can be expressed as a linear combination. Namely, the following is true. So theorem. So let AB belong to Z, not both 0. Then GCD of AB, or simply AB. I'm going to use between these two notations. I'm going to flip between these notations all the time. So this guy, GCD of AB, is the least positive integer that is a linear combination of AB. So this theorem tells us the following. This theorem tells us two things. One, that GCD of AB can be expressed as a linear combination of A and B. And not only that, if you take all the linear combinations, it is the least one among those linear combinations. Okay. So the proof goes as follows. So proof, let D be the least positive integer that is linear combination of A and B. Now, such a thing, we should argue that such a thing exists, right? So why does such a thing exist? So basically consider the following. So consider the set of all linear combinations. So let's take set of all AM plus NB, where M and N belong to Z. and take this guy such that this forms a subset of N. Okay. Well, we can modify the definition. B and AM plus NB belongs to N. Yeah. So this is again a subset of N, right? Why? Right from here, right? You're taking these combinations, you're taking all those belonging to N such that AM plus NB belongs to N, right? So now take this set S. Now claim S is non-empty as either A dot 1, if A is A dot 1 plus B times 0, or A dot minus 1 plus B times 0, or A times 0 plus B dot 1, or A times 0 plus B dot minus 1, as either of these guys belong to S. Now note that the reason for writing it like this is that we have that not both are 0. So one of them is non-zero. And if it is negative, then the multiplication by negative number will make it positive. If it is already positive, so we have A times 1. So one of them belongs to S. So S is non-empty. So therefore, by well-ordering principle, so recall what was well-ordering principle. Any non-empty subset of S has a least element, right? So by well-ordering principle, S has a least element. Yeah, so that is D. Call it D. All right. Now D will be of form. Okay, so D will be of form. So some linear combination of A and B. So let's say D is of form alpha M plus beta B. Sorry, alpha A plus beta B. It's a linear combination of A and B. Right. Now we want to show that what that claim D is equal to D is equal to GCD of A and B. Now we want to show that first. So two parts. That means we need to show two things. That is to show first D divides A and D divides B. And 1, 2, D is the largest integer. Such that D divides A and D divides B. Okay. So we need to show these two things. So 1. So what do we have? We have D equals to. So we have D equals to alpha A plus beta B, right? So let's take A and divide it by D. So it's gonna be QD plus R, where your R is between and is less than D. Okay, this is a consequence of Euclidean algorithm. Right? So if you divide, you can basically get this. Now R is either 0, right? Let's see what is it a possibility for R to be non-zero. So note that R is same as A minus QD, right? You bring it on the other side, which is going to be A minus Q times. Now what is alpha? alpha is, D is alpha A plus beta B. That is going to be, now organize this guy. So we get 1 minus Q alpha times A minus Q beta B. So now this belongs to your set S, right? Isn't it? Because after all, it's a linear combination of A and B. Now, also, so it belongs to S. Also, R is less than D, right? But D is the least positive integer, or D is the least element of, D is the least positive integer such that D belongs to S. So therefore, what? Therefore, R cannot belong to S, and the only way that can happen is, this implies R must be 0. Because if R is non-zero, it will belong to S and it's less than D, which will give you a contradiction. So therefore, R is 0. So this would imply D divides A. Yeah. Similar argument can show that D divides B. Now we want to show that D is the largest or the greatest common divisor. So for part 2, let C be a common divisor of A and B. This means C divides A and C divides B. But by using, if C divides A and C divides B, we have already proved that C divides the linear combination of them. That means C divides what? MA plus NB for all M and N belonging to Z. In particular, C divides when M is alpha and N is beta B, right? This means C divides what? C divides D. Now, this would lead to what? This would mean that C is less than or equal to D. That is, D is the largest of all common divisors of A and B. So this would mean, this implies D is equal to the greatest common divisor or the largest common divisor. So that means D equals to GCD of AB. Now, this is a very powerful identity. You'll see that why later on. Being able to write as a linear combination will help you to solve certain linear equations called linear Diophantine equations. But let's mention an outcome of this theorem, which is called Bezout's theorem. So we can write it as corollary. It's called Bezout's theorem. Bezout's theorem. Let A and B belong to Z. Then there exist two integers x and y belonging to Z such that GCD of A and B can be written as AX plus BY. So this is what the Bezout's theorem is, all right? Or whatever. You would also call it Bezout's identity. All right. So next theorem. Now this is about characterization of set S. So this set S has the least element of it is the GCD of A and B. But what are the other elements of it? So basically it says the following. So if you look at the set S, then it's all linear combinations. So set S is all linear combinations of A and B, and those linear combinations are essentially multiples of integer multiples of the GCD. That means what? So again, theorem, let A and B, in this case will restrict to the positive integers, belong to Z plus or set of natural numbers. Then set of all linear combinations. So set of linear combinations of A and B is the set of integer multiples of AB. So how do we prove it? So proof, so let D be equal to GCD of AB. Now we have D divides A and D divides B, right? Because D is GCD of A and B. So this means what? D divides MA plus NB for all M and N belonging to Z. Yeah. This would imply what? dk equals to MA plus NB, yeah, for some k. What have we shown? You have shown that if D is a GCD, then D would divide any linear combination. We have shown that any linear combination is a multiple of D. That is, any linear combination of A and B is multiple of what? Multiple of D. Now we have to show conversely. Let dk be any multiple of 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 D, right? Any integer multiple of D. Now we want to show that it's a linear combination. That's not hard to show because of Bezo's identity, we have D equals to alpha A plus beta B for some alpha beta belonging to Z. Now multiply both throughout by K, we get dk equals to alpha Ka plus beta Kb. This implies what? dk is a linear combination of what? Of A and B. And this proves our result that any linear combination is a multiple of D, and any multiple of D is a linear combination of AB. So they are precisely the same set. All right. Now comes another result. So there's another characterization of this. So theorem. So let A and B belong to Z, not both 0. Then D is the GCD of A and B if and only if one, D divides A and D divides B. So that is obvious to happen. 2, if C is any integer, with C divides A and C divides B, then, if then, right? So if this is the case, then C divides D. So note that many books take this as a definition, as a definition of GCD. All right. So now let's try to prove this. So proof is pretty straightforward. Proof, let D be GCD of A and B. Therefore, this implies D divides A and D divides B. That is by definition, right? Because after all, it's a common divisor, greatest, but still common divisor. So first part is okay. Now, we know that. So out of this, we also know that there exist alpha and beta belonging to Z such that D equals to alpha A plus what? Plus beta B. Why? Because of the Bezoos identity of Bezoos theorem. Yeah. So now we want to show, let C divide A and C divide B. This would imply, so now this would imply C divides linear combination of them, alpha A plus beta B, right? But this would mean C divides D because A alpha plus beta B is D. So therefore, you have proved both 1 and 2. So 1 and 2 is proved here. Now, we want to prove conversely. So other way around, conversely, let 1 and 2 hold. What holds? That is, what? That is D divides A and D divides B. And if C is any common divisor with C dividing A and C dividing B, then C divides D. We want to show that whichever D which satisfies this is a GCD. Okay, so how do we prove this? So let's prove about it. So from the part 1, we can see that D divides A and D divides B. So all we need to show is that D is the greatest of all common divisors. So now note that let C be any common divisor of A and B. This implies C divides D. This means what? C times some K equals to D, where K belongs to Z. Now, you can basically think about it in the following way. Now, K can consist of, so any positive, whether we'll get C is less than equal to D, right? Why? Because now consider the case. Now, if C is any common divisor, let's take only the positive ones, all right? We don't worry about the negative ones. So if we take only all the positive divisors, so you will get that CK equals to D. So that means what? That means where K belongs to. So if you only consider the common divisor, let's take to be positive common divisor. In that case, what will we get? We get k is greater than 0. So this would mean that c is less than or equal to d. So d is the largest, is greater than any divisor. So this would mean if I want to read this statement, I would say d, so d is greater than, is greatest amongst any common divisor, is greatest among common divisors of a and b. Therefore, d equals to GCD of a. Okay, so the conversely is pretty straightforward. Okay, so this basically, as I said, this is, many books take this as a definition of GCD. All right, which one to take? It's up to you. We would rather prefer, so to keep everything in order, we should use the definition given at the start of this lecture as the definition of GCD. Now we can extend this definition. So instead of talking about GCD of 2, why can we not talk about GCD of n integers? So again, let's have the following definition. So the idea is definition. So let a1 all the way until an belong to z. That means the integer, not all 0. Because if it is all 0, we'll define it to be 0. Right? Then greatest common divisor of these integers, of these a1, a2, an, these integers is the largest integer that divides all of a1. So this is called basically the greatest common divisors of these integers. Okay. So here we have the following lemma. So lemma. Now we need a way to compute them, right? So the way to compute them is given by the following lemma. The lemma is if a1, an, these integers belong to z, not all 0, then GCD of, or let me use this notation, a1 an is same as a1 an minus 1 an. Now, how do you interpret this statement? You interpret that if you take GCD of 2, you can combine any two and take GCD of them, and then replace them by their GCDs. So what do I mean by that? Say, for example, so before I go into proof of this lemma, example, suppose I want to compute GCD of 12, 18, and 30. So this is going to be same as GCD of 12, 18, 30. So now I'm computing GCD of two numbers instead of 3. GCD of 12 and GCD of number 12, and the second number is GCD of 18 and 30. So let's see. So what is GCD of 12 and 18? So 6, 3s are, sorry, 3 6 are 18, 6 5 are 30, right? So this is going to be 6. And what is the GCD of 12? And so this is going to be 6. So this is a GCD of these two guys, all right? And note that the order is not important here. right? AI is A1, A2, A, and order is not important. You could have also done this in the following way. You could have said 12, compute this. We get what? 630. GCD of 630 is 6. Now note that here also A1, A2, AN, the ordering is not important, all right? Okay. So, all right. So this takes care of the GCD. Now let's see how to compute the linear combination or how to use the Bezos theorem, right? So we already recall the Euclidean algorithm. So what was Euclidean algorithm? So Euclidean algorithm to compute GCD is the following. So how do we go about computing using Euclidean algorithm for GCD? Let's work with an example first. Say, let's take an example from textbook. So 252 and 198. We want to compute GCD of this. So what is GCD of this? So what we'll do is we'll apply a Euclidean algorithm and see what is the GCD. So let's divide 128, 252 by 198. So it goes 198 times 1. So 198 times 1, and then the remainder is 252, and then 2 from here. So that makes it 54. Now what you do is 194 divided by 54. So you divide it by 54. What do you get? 54. So 54 ones. So we'll go in 3 times, right? So 3 times. So 54 times 3. And the remainder is going to be, so 54 times 3 is 3 times 5. So 3 times 162. So 198 minus 162 is going to be 36. Then you divide what? Then you divide 54 by 36. So it's a good idea to keep them in this order. So we'll keep them in order. So 3 times 54 so that we can read them properly. So 54 is equal to, so how many times does 36 go? So only 1 times, and then the remainder is 4 here, and then 4, 8, 18. And then you have 36 equals to 18 times 2 times 18 plus 0. So in that case, this guy is the GCD of 252 and 198. So this is a Euclidean algorithm for computing the GCD, right? So for that, so we will prove this in a minute, why this process works. But before that, this process also helps us. So suppose 18 is GCD, 18 is equal to GCD. So 18 is GCD of 252 and 198. Now we can also use, so find one. We already found this 18. Of course, I need to prove this, why this is a GCD. I'll prove that appealing the theorem, Euclidean algorithm theorem, but find x and y such that 18 equals to 252x plus 198y. This is basically finding the x and y such that this holds. So some kind of x and y which satisfies the Bezo's theorem. So how do we go about it? So we start from this second last part here. So we write 18 equals to 54 minus 1 times 36. Now what you do is you have written this. Now you go one step up, right? And now once you go one step up, you'll see what is above 18. You have 36. So now replace 36 in this equation by 198 minus 3 times 54. So what I'm going to do is I'm going to replace 36 as 198 minus 3 times 54. So what do I get out of this? So I will get this minus this, so minus minus plus, so 4 times 54. Note that I'm not going to multiply it out. I'm going to keep these numbers appearing here as it is. I'm not going to get rid of them, right? And also these guys. So I get what? Minus 1 times 198, right? So we need to decide what to keep in bracket. Maybe it's a good idea to keep 98 in the bracket. Now I'll go one step up and I'll replace now 54 by 252 minus 198. So I'm going to replace here as 4 times, instead of 54, I'm going to replace it by 252 minus 1 times 198. Now I get what? I get 4 times 252 minus 4 times this minus, so minus 5 times 198. So that is 18. So your x and y, therefore x and y, what are x and y? X equals to 4 and y equals to minus 5. So this is how you find x and y which satisfy the required. Okay. So now comes the Euclidean algorithm, right? So what is a Euclidean algorithm? Euclidean algorithm is about computing the GCD here. Euclidean algorithm is basically a theorem. It says the following: you start with R0 equals to A and R1 equals to B. And you have A and B are greater than 0. Let's just take these to be greater than 0. All right. So now we'll apply what? So we can apply. So note that we can apply. We'll divide R0 by R1. So we get R0 equals to R1 times some Q. So let's call it Q1. And then we get R2, right? Some remainder R2 where R2 is less than R1 but greater than equal to 0, right? So now let me generalize this. This is just a statement. So I should write this statement in general indices. So if apply division algorithm, to get what? R, now here, say Rj is divided by Rj plus 1. The quotient is Qj plus 1. And the remainder is Rj plus 2. And what is the condition? With what do we have? We have Rj plus 2 is going to be less than Rj plus 1. And suppose this is greater than 0. So suppose it's an n-step process for j equals to 0, 1, all the way until n minus 1. And suppose we get out of this, we get Rn plus 1 equals to 0. After doing the in nth step, we get it equals to 0. Then we have GCD of A and B is that one step before Rn plus 1. That means this is Rn. Okay, the last non-zero remainder. Right. Now, why is this true? So for that, let's basically have the following lemma. The lemma is let D and this are integers, where E equals to dq plus R, where Q and R are integers, then ED, GCD of E and D is same as GCD of E and R. Yeah, the proof follows from, the proof is actually straightforward application of this theorem here. The first few theorems we saw, namely, the following theorem here, right? That AB is same as A plus C, GCD of AB is same as A plus CB comma B. So GCD of AB is A plus, GCD of AB is same as GCD of A plus CB comma B, where C is any integer. We don't care what integer it is. These GCDs will be the same. So the proof is going to be, so proof is just follows from that. Or if you like, we can say GCD of ED is same as GCD of E minus, sorry, GCD of ED is going to be GCD of E dq, or E plus D of minus Q, comma what, comma E, right? So that is going to give us, this is going to be, however, I want, okay, of course, on one hand, this is true, but I want that this is true, all right, because it should satisfy this. I'm basically playing this Euclidean algorithm game, right? So I get E plus, so I should change this. So I get GCD of E comma D is going to be E minus, so I need what? ED, I need this to be DR, right? So DR, so I can do GCD of this is going to be E minus DQ comma D. That means this is going to be RD, but GCD of DR is same as RD is same as GCD of DR. GCD of AB is same as GCD of BA, right? So therefore, done. Now, the proof of Euclidean algorithm. So the proof of this algorithm, so proof of Euclidean algorithm is just application of this over and over again, right? So proof of Euclidean algorithm is let R0 be A, R1 be B, right? So then we can do the following. We can have GCD of AB is going to be, first of all, GCD of R0, R1, Now this is going to be GCD of, now I'm going to replace R0 by, what should I replace R0 by? I'm going to replace R0 by R0 minus Q1 times R1. So R0 minus Q1 times R1, comma R1. And what is R0? So we have R0 equals to Q1 R1 plus R2, right? So in this case, this will be replaced by GCD of R2 R1, which is same as GCD of R1 R2. And I continue this process until the end. I'll get this is equal to, I'll keep on repeating this process. I'll get GCD of R n minus 1 Rn, which is going to be GCD of Rn minus 1 times Qn. So Rn minus Rn Qn, comma Rn. Now this is going to be 0, right? What is Rn minus 1? So here you see that Rn plus 1 is 0. So we'll get, this is same as GCD of 0 Rn, and Rn is non-zero, right? It's the last non-zero remainder, and that is same as Rn. So now let's do another example. GCD compute GCD of, so let's do 252 again and 198. But this time we'll write down the steps of Euclidean algorithm properly. Okay. So let's see. So we'll have J, we have R J, right? So J is 0. We need Rj plus 1. We need Qj plus 1. We need Rj plus 2. Now, why this table choice? Note that Rj equals to Rj plus 1 times Qj plus 1 plus Rj plus 2, right? This is what the Euclidean algorithm looks like. So we should list all of them. We're computing these guys, so let's list them. So j equals to 0, we have Rj, which is the first one, 252, 198. And then when you divide them, you get 1, you get remainder to be 54, right? So you divide 254 equals to 198 times 1 plus 54. Now step this guy, this will come here now. This becomes your new. So 198, this will come here. You have 54. When you divide, you get, what do you get? You get 198 equals to 54 times 3 plus 36. So I get here, so 3 and then 36. Now again, what do we get? Step 2, this will come here, right? This will come here. So what do I get? I get 54. Now I'm dividing it by 36. It goes 1 times and the remainder is 18. Now step 3, I get 36 here, dividing by 18. It goes 2 times, remainder is 0. So this guy is your GCD. So this is how the game is played. All right. So that's about it, folks. Talk to you soon. Thank you.